Hi there, welcome to Raelene Maths. Why is a line straight, and why does it have the equation y equals mx plus c? Let's consider this line that passes through lots of points, but I'm going to use these 2 points, which are easy to read from the graph, and drop a vertical line down and a horizontal line across until they intersect at a right angle. I've now made a right triangle that has an altitude or height of 3 and a base of 4. It also has been inclined a certain amount from the base to the slant or diagonal hypotenuse of the right triangle. Now we can consider another line that passes through some of the same points and also forms a right triangle. This right triangle has the same base of 4, but now it has an altitude of 2. And we can see that the green line has been angled from horizontal by a smaller angle. And so we are going to define the steepness of a line as the gradient or the slope of the line. And we are going to let that number value for the gradient or the slope be called m. Not because there's an m in either gradient or slope, but because it comes from the French monter, like mountain, to climb. And we are going to calculate the gradient as a ratio of the height over the base. So we can see for the blue line, the height over the base is 3 over 4, which is a greater number than the green gradient or slope of 2 over 4, which is the same as 1/2. But not all lines increase from left to right. They don't all go up. And so how are we going to deal with a line that actually goes down from left to right? Well, here we have another line that's going down, and we can pick 2 points on this line, such as -1, 7 and 5, -1. So when we want to calculate the gradient of this line, I still personally always consider drawing a right triangle. And if I drop a vertical line down and a horizontal line across, I can see a right triangle. But this time, direction matters. Because we are going down and then we are going to the right, we don't really want to calculate the height, but we want to calculate the directed height. And similarly, we want to calculate the directed base. So we are going to define the gradient, or the slope m, as the change in height over the change in base. Let's call the first point point A and the second point B. Now we have the gradient of the line through points A and B as the change in y from A to B divided by the change in x from A to B. And when we calculate this, we take the second y coordinate, which is -1, subtract the first y coordinate, which is 7, divided by the second x coordinate, which is 5, subtract the first x coordinate, which is -1. And this gives us a gradient of -8 divided by +6. And what that's telling us is that we're going to go down 8 spaces and then to the right 6 spaces. And those are instructions on how we will move to generate a second point on the line from a first starting point, such as point A. But what if we want to start at point B and go to point A? We would have to reverse the direction. We would have to go 6 spaces to the left and 8 spaces up. And that would cause the sign of the numerator to change and the sign of the denominator to change. But these two fractions are equivalent. In fact, we could factor out a 2 from the top and the bottom and be left with a simpler gradient of -4/3. This tells us that we could go down 4 spaces and then right 3 spaces and get a point that lies on the line. But in fact, we could do that a second time and go down 4 spaces again, right 3 spaces, and still get to a point that lies on the line. The fact that we made 2 of these blue right triangles shows up here in the common factor when we reduced our fraction or our gradient. This is at the heart of why a line is straight, the fact that we have these equivalent fractions and similar triangles. So now we understand a little bit more about the steepness or the gradient or slope of the line. We still don't know why it's multiplied by x, and we don't know where plus c comes from. Let's take a look at that in the next slide. Now that we've defined the gradient, we need to come up with a true statement, one expression that equals another expression for all points on the line, so that we can come up with this equation. We'll start then by picking 2 points A and B and dropping a vertical and horizontal line to form a right angle. Now we've got a right triangle whose hypotenuse lies on the blue line, or the line that contains points A and B. We'll pick another point C and form another right triangle with point A. And lastly, we'll pick a third point D and form a third right triangle. In fact, we can do this over and over for lines, because the essence of lines is that these 3 right triangles are similar. In fact, lines form families of similar right triangles, and it is this fact that we will exploit to be able to come up with the equation of the blue line. So what makes these triangles similar is that all three angles are the same. We have a right angle in each corner. Each triangle has been inclined from horizontal to the blue line by the same angle, and then if two angles in a triangle are the same, then the third corresponding angles must be the same. Therefore, we have similar triangles. And furthermore, we can see that we have a constant scale factor that resizes all the sides of one triangle to produce another. This means that the sides are in proportion, and we can say this in another way, that the ratios of sides form equivalent fractions. Specifically, let's take a look at the fraction formed by the gradient. The gradient is the height over the base, or the directed height, delta y, over the directed base, delta x. And we calculate delta y as y2 minus y1 over the delta x, which is x2 minus x1. Let's calculate the gradient for the hypotenuse of each right triangle. In the first right triangle, containing points A and B, the gradient is going to be y2 minus y1 divided by x2 minus x1. When we simplify this, we get positive 3 over 4. For the next right triangle, containing points A and C, we have y2 of 4 minus y1 of negative 2 over x2 of 3 minus x1 of negative 5, which gives us a gradient of 6 over 8. And for our last right triangle, which is the green one, we can calculate the gradient as y2 of 6 minus y1 of negative 2 over x2 of 7 minus x1 of negative 5, which gives us 8 over 12. Now, because these triangles have different sizes, the bases and the heights are different, and therefore so are the hypotenuses. But if we multiply the first fraction of height to base by 1 in the form of 2 over 2, we end up getting the second gradient, which is 6 over 8. In other words, the fractions 3 over 4 and 6 over 8 are equivalent. We could also multiply the 3 over 4 by 1 in the form of 3 over 3, which gives us the green gradient of 8 over 12. And because we are only multiplying fractions by 1, these fractions are equivalent. This is what we're saying when we talk about the sides being in proportion and the ratios of the sides forming equivalent fractions. So the gradients of the red, blue, and the green right triangles, those hypotenuse line segments, are the same gradient. This is the essence of being a line, of a line being straight. Furthermore, we can see that the 3 that we multiply the height by and the base by from red triangle to get the green one is that constant scale factor that we talked about when we have similar triangles. So now we can see that we can take two or more similar triangles that are formed from a line and make an equation out of their gradients. Let's see how to take this fact to finally come up with the equation of the line in the form y equals mx plus c. We finally have a truth about lines that allows us to come up with an equation. We know that ratios of sides of similar triangles are equal, and this is because we are able to come up with similar triangles using points on a line. So I'm going to come up with the gradient from points A to B and set that equal to the gradient from point A to P. The gradient then from A to B is going to be y2 minus y1 over x2 minus x1. And then the gradient from A to P, we could also go from P to B or any other point that we choose, but I'm using P here as a variable point whose coordinates x and y can vary, can change, whereas x1, y1 and x2, y2 are fixed numbers for points that are definitely on the line. We might also come up with another name for point A. We might give its coordinates the letters A and B, or we might give it letters H and K, or really any other letters that we want. I'm going to use H and K instead of x1, y1. And so we come up with y minus k divided by x minus h. Now we know that these two things are equal, and in fact they are equal to the gradient m. So instead of using y2 minus y1 over x2 minus x1, I'm going to call this m, and it's equal to y minus k divided by x minus h. To make the equation look a little simpler, I will clear the fraction by multiplying by x minus h on both sides, and then rearranging, I can isolate for y minus k to give the equation y minus k equals m times x minus h. This is known as the point slope form or the gradient point form of a line, and it is one step closer to finding out how we come up with the equation y equals mx plus c. If instead of having any old point A at h comma k lying anywhere on the line, we know specifically that the point is located on the y-axis, we could call that a point C. It has an x-coordinate of 0 and a y-coordinate which we might call little c for constant. Then, instead of substituting h comma k in as the known point on the line, we would replace h with 0 and we would replace k with c. This gives us the equation y minus c equals m times x minus 0, but x minus 0 is just x. Lastly, if we rearrange to isolate for y, we end up with the equation mx plus c. So it turns out that y equals mx plus c is a special case of the point slope or slope gradient form y minus k equals m times x minus h. This equation is general because it allows us to use any known point on the line, h comma k, whereas y equals mx plus c is a special case of the equation of a line where the h comma k has been replaced with 0 comma c. Specifically, if the x-coordinate is 0, we have a special case. So if you were only to learn one form of the line, it would be the y minus k equals m times x minus h form, because it allows us to use any point on the line and not just the y-intercept. Well, there we have it. We finally come up with why the equation of a line is given by y equals mx plus c. Check out the next video where we take a look at some examples involving lines and points on a line. Thanks for checking out Raelene Maths.